So good morning. Um, so this is a 6-hour lecture series on computer architecture. Again, in this series, we will be concentrating on certain specific aspects of computer architecture. The subject matter for this lecture series has been discussed with the faculty members, and we have converged on certain topics which are of interest to the colleges, and that broadly includes the memory and the IO subsystem of computer architecture. So I will be concentrating on the memory as well as the IO of aspects of computer organization. So this current lecture, which is of 2-hour duration, is organized as follows. We will start with the concept of memory organization, how a memory is organized, okay, and various memory technologies that are prevalent today and commonly being used. So we will briefly touch upon different memory technologies that includes the ROM, read-only memory, and its variations like programmable read-only memory and then EEPROM and so on. Then we will discuss two important kinds of memory. One is the SRAM or static RAM, and another is the DRAM or dynamic RAM. After completing our discussions on memory technologies, we will get into the concept of memory hierarchy. What is the need for an hierarchical memory structure, and what is the design problem that we can specify when we design a hierarchical memory system. So first we will start up with getting a conceptual understanding of what memory is, how memory helps us in storing and retrieving data. So conceptually, you can look at a memory as a set of registers. A register is the one which can store a group of bits, and a bit can be stored using a flip-flop. So this is how we store a number of bits, organize it as a group called word or data, and store a number of such words in different locations, which we will call it as address. So here you can see a memory consists of a number of locations or registers. Each location has to be given a unique address, which is a unique identifier, and in this case we have taken an example where the memory has got 1024 address locations. So if you use a decimal to denote the address, then it will range from 0 to 1023, so 1023. The corresponding binary equivalent of these address would be a 10-bit address starting from 10 zeros all the way to 10 ones as follows. So this is the address that we allocate for the different memory locations. Each of this memory location can store a group of bits. Again, the bit of the data can be varying. It can be just 1 bit for certain kind of memory, or it can be 8 bits or 16 bits or 32 bits. So in this example we have seen a group of bits, okay, probably of 16 in length. Here you can see that the address 0 stores the content which is as follows, that is 101101 and so on. So we have stored 1024 different data item, 16-bit data item on 1024 locations. So if you conceptually how a memory will work is, we can do two operations, one which we call it as the reading, another called as the writing. So to begin with, we can write a content into a memory address location by providing the address and the corresponding data to be written and enabling the command. In this case it has to be a read command. So if you do so and give some time for the memory to store the result, then the data will be written into that location. So if you view the memory to be a black box, which is as shown here, then it has got the following lines which goes inside and come out. One is the address, a group of address lines. Let us assume that there are k address lines. This group of address lines are related to each other because they all represent different bits of an address. So together these lines form what is called as an address port. The width of the address port or address bus is k in this case. So there are 2 power k different memory locations that are present in the memory. Then data can be written into or it can be read from. So we have got n data input lines and n data output lines. There are 2 control signals. One is the read, another is the write. So the way we have to make use of this memory module is that provide the k address in the address bus, okay, which is connected to the address port of the memory. Then enable the read control line, then wait for some time for the data to be available in the data bus output port, then take it outside. If it is a write operation, provide the address bus, provide the n data bits to be written into, enable the write command and wait for the data to be written. More often what happens is there is no separate lines for data to be inputted and separate lines for data to be taken out. Both these 2 data buses are being multiplexed on the same bus, because at any given time we will do either a read operation or a write operation. So we can have a bidirectional bus connected to a data port of width n. So both read and write takes place only through this bus. Normally, in addition to these 2 control lines, read and write, there can be a separate control line called as the memory enable line, ME line. Okay, this line is used to enable or disable this memory, because there can be a number of such modules that may be interfaced with the processor, out of which only one has to be used at any given time. The memory module which is to be used has to be enabled, others have to be disabled. In order to facilitate it, we need this control line. So that memory enable line is not shown in this particular module, but if you include it, then the way the module will work is shown in this table. So we have a memory enable line. If it is 0, the memory is disabled, in which case the read or write logic, whatever it may be, 0 or 1, no operation will go on. That is why we don't care what the read or write control line will, no operation will go on. On the other hand, if the memory is enabled, that is when memory enabled is 1, then a 0 will perform a write operation and a 1 on the read bar write will perform a read operation. Again, a point to be noted is we can have 2 separate control lines, read and write, as shown in this diagram, or there can be a single line, okay, which can be like read bar, write bar, R bar, write bar. So if it is 1, then it is a read operation. If it is 0, then it is a write operation. Then we will move on to the next slide. Here we see how a read or read operation will go on. That we will see by using a timing diagram, and we call this as the read cycle, and we will see it in terms of the basic clock that drives the processor. In terms of the basic clock, at various clock periods of the clock, what are the operations, how the signal changes and what operations get carried out. Normally we refer these clocks as T states when it comes to the processor. So we will distinguish them as T1, T2, T3. Okay. For the present, let us assume that it takes 3 clock periods for this read cycle to go on. So we have shown against the clock signal the different related lines in the form of separate line or bus. One is the memory address bus, another is the lines which is memory enabled, then the read write control lines and the data bus. So at the beginning of the read cycle, the address is placed on the memory address bus. Okay, so it changes and it is present for the entire duration of the read cycle, which is 3 clock periods. Then the memory is enabled, okay, by making it high. Then the read bar write, in this case this is made 1 because When it is 1, it means a read operation. So actually the figure has to be something like this one. So it is asserted as 1, then the address is present, the memory is enabled, the read command is given. So it will take some time for the memory to fetch the data from the location and place it on the data bus. So this is the time at which the data becomes valid, and within this duration the data has to be latched outside. So this is how a read cycle works. Coming to the write cycle, it is very similar to the read cycle. Again we will assume that it takes 3 clock periods for the write cycle to get over. Of course it depends upon the speed of the memory. If a memory is slower, we may need more clock periods and so on. So again, for the write cycle, the valid address has to be placed and be present throughout the write cycle. Then the memory is enabled again by asserting it to 1. Then the command is given as it is a write command. So read R bar W bar becomes low, and then the data to be written is placed at the beginning of the cycle, the write cycle itself, and maintained throughout the cycle. Well within these 3 clock periods, the memory will write the data into the memory location. Okay, for example, this is where we can be sure that the memory is being latched inside, and after that we give a safe period for memory to be the data to be changed. So this is the write cycle. Next we will see how the memory stores the various bits in it, and thereby we will see how the different technology enable the bits to be stored in memory. We will see how conceptually a bit can be stored in a flip-flop, and then we will make use of it and then construct a register which can be used as one location in a memory, and then we will put a number of registers together and construct a memory, and we will see how the locations can be decoded and so on. So we can see that a flip-flop can be used to store a bit. We can make use of a SR or the set reset flip-flop to store a bit. So here is a memory cell which stores a bit using an SR flip-flop. It has the following control lines. One is the select control lines. Only when the select control line is 1, the memory will be selected. If it is 0, then the memory will not be selected. Then there is a control line, read bar write. Okay, if is actually we can make it like this one. If it is 1, then it is a read operation. When R bar W bar is 0, then it is a write operation. If you are going to write, the input bit to be written has to be given in this control point, and if you are reading, the output will come out of this point. Okay, so conceptually this is shown in the form of a black box, or we call it as the bit cell, where there are 4 signals. One, the select line, then the read bar write control line, then the input line to write a bit, output line to read a bit. Now let us see how this memory cell works. First, when the select line is 0, okay, you can see that this AND gate and these 2 AND gates are disabled, because the select line goes as one of the input to all these 3 AND gates. So this AND gate will, the output of the AND gate will always be 0. Okay, this is being disabled. Similarly, because the input to these AND gates are 0 0, the set and reset will have 0 0, and therefore the flip-flop will not change the state. On the other hand, when this select line is 1, then all these gates are enabled. Now let us see, under this condition, when the bit cell is being selected, what happens when the read bar write bar is 1. We can see that when the read bar write bar is R bar write bar is 1, then this cell is enabled, because this line will enable this. Then the Q output of the SR flip-flop, we will have normally 2 outputs, Q and Q bar, which are complement of each other. The Q output of the SR flip-flop, okay, is being placed on the output, because the select is also 1, the read is also 1, the value that is stored in this flip-flop will be available at the output. So this is how we read the content of the flip-flop. On the other hand, when R bar write bar is 0, then this flip-flop is disabled, this AND gate is disabled, whereas 0 here will place a 1 here, and both these gates are being now opened. Then the input bit, okay, and its complement will be available to S and R inputs of the flip-flop respectively. So when the input is 1, S will be 1 and R will be 0, and the flip-flop is set, which means it stores the bit 1. On the other hand, when the input is 0, then a 0 will be present in S and a 1 will be present in R, and the flip-flop is reset and a 0 bit is stored in the flip-flop. So this bit cell can be used to write a bit into a cell or read from it, and we can have the option of selecting it or not selecting it. Now we can put a group of these bit cells to construct a register and a group of registers to construct a memory. As a simple example, we will see how a memory of 4 address locations, each storing 4 bits, can be constructed. So we will have an array of 4 by 4 bit cells as shown here, and we need a mechanism to select. So these 4 cells which are present in a given row form one address location, another such 4 bit cells will form another address location, and so on. So we have got 4 locations, they are numbered as 0, 1, 2 and 3. So there are 4 locations, and therefore we need 2 lines to select one of these address locations. So the address bus has 2 bits, is 2 bits in size. So we use a decoder which is a 2 to 4 decoder, which takes this address lines, 2-bit address lines, decodes it and generates asserts only one of the output of this decoder as 1. So only one of these output will be 1. Call this as word 0, word 1, word 2 and word 3, because there are 4 words that are present in this memory module. We also have a memory enabled control to this decoder. When the memory enable is 0, the decoder will make all the word lines as 0. None of the location will get selected, and therefore the memory will not perform either a read or write operation. On the other hand, when the memory is enabled, the decoder is enabled, and based on the value that is present on the address input lines, only one of the word is being selected, and the selected location, let us say we select word 1, then the selected location, okay, is available for us to perform a read or write operation. So you give the corresponding operation read or write in this line. So it goes to all these locations, and if it is a read operation, then the output that is being read from the corresponding bit cells, in this case it is 1. So these will be available and through these OR gates, because each one of these OR gate is a 4 input OR gate which will OR the outputs from each of the bit cells in the corresponding address location, and the values will be available on the output data port. On the other hand, we can write by asserting a 0 on this read bar write bar and give a valid input here. Then let us say we are writing into the location 3, then these bit cells will be selected, and the data that is being returned will be available at these places, and on giving the corresponding this line to be 0, the values will be written into this flip-flops, corresponding flip-flops. Well, now let's look at the case of this memory. It works perfectly well, but if you try to scale it up, let's see what problem arises. This is a very small memory, at least we want a little larger memory, let us say of size 1 kilobyte. Then each location has to store 8 bits. So 8 bit cells can be placed in each address location, but there has to be 1024 locations, for which we need a decoder which is a 10 to 1024 decoder is what we require. Okay. Now let us look at the complexity of constructing a 10 to 1024 decoder. If it is a 10 to 1024 decoder that we have to construct, it should have AND gates, each of 1024 AND gates, each of it has to be a 10 input AND gate. Okay. So the complexity of the decoder is very large. So this is just for 1K. If you are going for a 64K or 1 MB, then it becomes impossible to have such kind of decoders. So in this case, we can have a 2-dimensional decoding mechanism. So what we do is, instead of having a 10 to 1024 decoder, we make use of two 5 to 32 decoder. One we use as a row decoding, another for using column. So we need a modified bit cell now. So each of this bit cell should have 2 select lines and not just one. Okay. So one is called as the row select, another is called as the row select, another is the column select. Only when both these row select as well as column selected are selected, the bit cell will work. Now what is the advantage? It allows us to do what's called as the 2-dimensional decoding. So the entire 10 address lines are divided into 2 groups of 5 each. Okay, one we call it as X, another we call it as Y. The lower order, let us say 5 lines which represent the X, is given to a 5 to 32 decoder, and it selects one of these rows, while the higher order 5 lines which we call it as Y as given to a 5 to 32 decoder, which will select one of these columns. Therefore, for a given address which is a unique 10-bit address, one row and one column is being selected, and therefore only one cell is being selected. For example, if X is of this value and Y is of this value, one of these the 12th row and the 20th column is being selected, and only this bit cell will be selected. So in this bit cell, now you can perform a read or write operation. So now it's a case where the complexity of decoding is largely reduced, because we need only 2 5 to 32 decoders, and each 5 to 32 decoder we need 5 input AND gates. Totally we need 64 5 input AND gates, which is much less as compared to 1024 10 input AND gates. So the decoding becomes easy. But what happens here is that each such cross points now had got only 1 bit cells. So only 1 bit can be stored in each location. If we need more bits to be stored, each cross point should have more bit cells. Normally we will have only 1 bit cell to be present here, which means that we can construct memories of this one, but each location can have only effectively storing only 1 bit. If you want to construct a byte, 8 such memory modules have to be used in tandem. So normally DRAMs are constructed in this manner. Now if you have a larger memory of size, let us say 64K DRAM, each location storing 1 bit, then it has got 16 lines, which will be divided into 2 groups of 8 each. There will be 8 lines for the purpose of row selection, 8 lines for the purpose of column selection, and therefore we can have 8 to 256 decoders here, one for row and another for column. Okay, and these 256 by 256 array of bit cells can be used to construct a 64K memory. And normally, but what happens here is, in this case, if you have this kind of a memory chip, then if you give all the 16 lines that represents the address, then we need 16 input pins that should come out. In addition, we should have control lines and for the data, the number of the pinouts may be very large. In order to reduce that, normally what we will do is we will provide only a row data or the column data at a given time and store it internally so that it can be used at the actual time of reading or writing. So we will effectively have only an address port of 8 lines. First we may provide the row data, row address, which is the, for example, the 8-bit row address is provided, and that address is stored in this register. For that we will use a signal called as the row address strobe. So the row address is being provided and the row address strobe is being given. So this stores this 8-bit row address, and the 8 to 256 decoder will select one of the rows. Then we will change it to the and place the column address and enable the column address strobe. So the column address is being stored in this column 8-bit column register, and the 8 to 256 decoder will decode it and select one of the columns here. So the corresponding cross point, the bit cell that is present, will be selected and the data can be read out or written in based on the read bar control logic that we provide. So this way we can construct larger cells. Now we will look at, having looked at how a memory can be constructed, then we will look at how such a memory can be interfaced with the processor. Well, now with regard to the processor which has a ability to interface with the memory, what are the relevant control lines that come out of the processor and the registers and the controls within the processor that enable this interaction to work. So here we show the CPU and the relevant registers and the control lines of the CPU, and also a main memory module. So the module, main memory module, has the following ports: the address port, the data port, read bar write control line, and then 2 more line, one to tell that to start the operation or request for the read or write cycle to start, and in turn the module gives out what is called as the complete line, which complete signal, which tells that the operation, after it gets over, it signals the processor that the operation is over. Within the CPU, the address has to be placed on the address bus, which is interfaced with the memory. For the same, it uses a register which is called the memory address register or MAR. Normally the memory address register will hold the address which will be placed on the address bus from which the read or write operation will happen. The data, if it is written, it will be placed in the memory data register beforehand, before the write cycle, or if it is a read cycle, then the data that is fetched from the memory will be latched into this MDR. So the MDR acts as the interface, memory data register MDR acts as the interface for all the data that comes out of the processor or goes inside the processor. The processor may also have some register files. So let us assume that the memory, the width of the address port is M bits. So the MAR is an M bit register and the width of the memory address port of the processor is an M bit, numbered from 0 to M minus 1. Width of the data, let us say if it is N, B, then the B lines is the width of the data bus and the data bits are numbered from 0 to B minus 1. So you provide an address and assert, let us say, a read command, and then wait for the data to be fetched from the corresponding memory location onto the data bus, and the data is being latched into this MDR. This is how the read operation goes. Similarly, the write operation can also happen. Next, when it comes to storing content into the memory and fetching it, we need to look at some other related issues. Normally, the processor reads in terms of 32 bits or 64 bits, which depends upon the size of the width of the data path of the processor. Suppose if it is a 32-bit processor, the bit of the data bus will be 32 bit. It will read 32 bit at a time. But normally the memory which is interfaced with the processor is byte addressable, which means every location in the memory stores only 1 byte, which means a 32 bit that is being read by the processor has to be stored in 4 different memory locations, which are usually successive in nature. Suppose we store a 32 bit which comprises of 4 bytes, then we should make use of 4 successive locations for storing it. Let us say we start storing the bytes in location 2000, then we have to use 4 locations 2000, 2001, 2002 and 2003 to store the 4 bytes. Okay. Then when the processor reads a 32 bit, 4 bytes are read from these 4 locations and transferred at one go. Now we need to have a convention of how we pack the 4 bytes, okay, of the 32 bit data in the 4 different locations. There are 2 conventions that are prevalent in the industry. One way of packing the bytes is called as the Little Endian way of packing. Another is called as the Big Endian way of packing. In the Little Endian packing mode, this is how the bytes are being stored. Okay. So in the Little Endian stores the least significant byte at the lower byte address, which means that if you have the LSB, the lowest significant byte, which has the bits 0 to B0 to B7 are stored in the lower significant address, that is here. Okay. So bit 0 to B0 to B7 are stored in 2000, B8 to B15 are stored in 2001. So 2000, 2001, 2002, 2003. If this is how it is being packed, then it is called as the Little Endian way of packing. The lowest significant byte is stored in the lower address. On the other hand, if the lowest significant byte is stored in the highest address, then it is called as the Big Endian way of packing. Different processors have different convention. For example, the Intel processors will have a particular convention, whereas the Motorola processors will have a different convention. So this has to be kept in mind when we store and retrieve data on the memory by the processor. Then we will talk about the different memory technologies. We will start with the simplest one, which is the read-only memory. This is the kind of the memory which is a non-volatile memory, which means that power is not required for the content of the bits, content of the memory to be retained. So even there is power goes out, as of the content that is stored in the memory will be retained. Then by the as the name indicates, we can only read from this memory and we cannot write and read. In fact, the write operation is being done at one time, and once written we cannot rewrite back into the memory. So basically the way, conceptually the way it works is as follows. Let us assume that it is a memory with 4 locations, each location storing 4 bits. So you have an address port of actually 2 bits which selects 4 different memory locations, which we can number it as 0, 1, 2 and 3, and there are 4 bits that are stored in these locations. So in order to do that one, what we have to do is we have to hard code the data that is being stored. So let us say this is the bit D0, D1, D2 and D3. Then what we will basically do is at each of these cross points we will enable an connection or disable the connection. If a connection is enabled, a bit is stored, okay, in a particular manner. We will see how it works. For example, let us say if the address 3 is being chosen, then let us see what happens. Then we have a plus B here, and we have at each of these cross points FET transistors, field effect transistors are there. So when the line 3 is being selected, the gate of this transistors are being asserted, then effectively it allows a conducting path from this plus V through this resistor to this ground, and current flows and the voltage get dropped here, and this will be close to 0. Whereas for these points there is no connection, so this will be close to 1. So again at this point this will be close to 0, and here there is nothing and it will be 1. So whenever there is a cross point, the corresponding line will be 0, otherwise there is a 1. So we can read out of it. So here we have a group of active low buffers. When there is a chip select bar is enabled, these buffers are being selected, tri-state buffers are being selected, and we have a bubble here. So whatever the content of it is being negated and given here. So effectively we will have a value 1010 being read out. So wherever there is a cross point, we effectively store a 1. Wherever there is no such cross points connection, we store a 0. So initially all these cross points will have this kind of a structure, and we selectively blow at those points where we don't want a bit to be present. So this is how ROM works. Then we have variations of these ROMs. Programmable read-only memory, which is programmable in the field or by the user. Then we can have erasable programmable read-only memory, which can be erased using an UV light. Then also electrically erasable programmable read-only memory, where it can be erased and written more than once, but it can be done in a convenient manner, wherein it can be done using an electronic, not using a UV but using electronic mechanisms. Okay. Then the next thing that we will see is, suppose we have got ROM, or for that matter even a RAM. Okay, how do we combine a number of such modules and have a larger memory which has got more address locations or more width of data width? Now let us say we have 2 ROMs. Okay, we are interested in putting 2 or more memory chips that can be combined to create more bits per locations. So each of this ROM is an 8x2 ROM, that which means it has got 8 different locations, but each location is effectively storing only 2 bits. How do we put 2 such ROMs and construct a ROM which has got 8 locations but stores 4 bits in each location? So this kind of an arrangement can be used for that. Because there are 8 locations, we need 3 lines to identify an address. So the address port has got 3 lines, which we denote as A0, A1 and A2. So we have 2 such ROMs. Each of these ROMs also has got an address port with 3 bits. So we connect A0, A1, A2 to these address ports of these 2 ROMs. Then both these chips are being selected. Chips enabled lines are being asserted for both these chips. The output enabled lines of both these chips are also enabled if read operation is what we want to perform. And then the data lines of both these chips are taken out. Each of this ROM has got 2 data lines. If you combine both of them, we will effectively have 4 data lines. So we can have effectively an address location, each of which can store 4 data bits. So we can number them as D0, D1, D2, D3 outside. The bits D0 and D1 are stored in this ROM. D2 and D3 are stored in the second ROM. So in each of this location, for example in address location 0, 2 bits are being stored in this ROM, while the 2 lower significant bits are stored in this ROM. So this way we can construct a memory which has got more data bits per location. Now we will look at the other problem, wherein we want an address which has got 15 locations, but each location storing only 2 bits. For that again we can use two 8 by 2 ROMs, the same thing that we used earlier, but the way we interface them will be different. So we use two 8 by 2 ROMs. Each of these ROMs has got an address port of 3 lines because there are only 8 locations in each of these ROM. They are represented as A0, A1, A2 in each of this ROM. Then the data port of each of this ROM has got 2 bits, D0 and D1. Now we tie the data port of both these ROMs. We don't take it out separately, we tie them together and we take one common data port outside. Then we, let us say for the purpose of reading, we can always output enable both these ROM using this OE line, and we at any given time we will select only one of these two ROMs using this chip select or chip enable control lines. So we can see that there are 8 locations in, let us say, ROM 1 and 8 more locations in ROM 2. We want to arrange them together so that whenever we use one more control line, which we will call it as A3, okay, based on that one of these ROMs are going to be selected. Let's see how it works. Let us see if when A3 is equal to 0, when A3 is equal to 0, then this chip is not selected, but you will enable this AND gate and this chip will get selected. So based on the values of A0, A1, A2, one of these location in this ROM 1 will be selected and the corresponding data will be made available on the data bus. On the other hand, when A3 becomes 1, then this ROM will not get selected, whereas when A3 becomes 1, so this gate is enabled and this ROM 1 gets selected, and based on the values A0, A1, A2, one of these locations in ROM 1 will get selected and the corresponding data will be available. So A3 basically works as an higher order address line. Okay, that is why we have called it as A3. So together A0, A1, A2, A3. For example, if we write it as A0, A1, A2, A3, based on the value, okay, as 16 possible values, 16 different locations are being selected. For the first 8 locations, A0 will be all zeros. For the next 8 locations, A3 will be 0 for the first 8 locations, which are numbered from 0 to 7. For the locations numbered from 8 to 15, A3 will be 1. So these 8 locations are mapped onto ROM 2. These 8 locations are mapped onto ROM 1. So this way we can construct memories of larger size. We can club both these techniques, this techniques and the previous technique, and even have a memory which can store 4 bits in each locations and having 16 such locations. Now let us talk about the static RAM or SRAM. Okay, so here the bits are stored using on-off switches. There is it doesn't use the concept of storing the bit as charges as in the case of DRAM. Therefore there is no leakage and therefore there is no need for a refreshing. We will come back to this factor again when we talk about DRAM, then it will become clear. But it is little more complex in nature because it involves more transistors and therefore SRAMs are costlier. Larger bit area is required, so it is expensive, but it is a faster chip, so it can be effectively used for caches. Okay, as a digital circuit, it basically used a mechanism of flip-flop to store a bit. So each core cell of a SRAM can be constructed by having 6 transistor circuits. The values are stored symmetrically, which means that both the bit and its complement will be available at any given time, and SRAM retains the value as long as there is power, which means that the chip has to be powered, but the bits at the content of the locations need not be refreshed. So the way the SRAM can be organized is very similar to the earlier organization. Okay, that is, we have an array of the SRAM cells forming a register, and we have a group of registers placed in the form of an array. We provide the address on the address port and make use of an address decoder which will enable only one of these different words in the SRAM. Okay, so for example, there are 16 words or 16 locations. Now we call them as word 0, word 1 to word 15. Only one of them is being, one of the locations is being enabled. Then the value that is stored in each of this cell, okay, its value and its complement value will both be available in two different lines, and we use a circuit called as the sense bar write circuit in order to for the purpose of reading from it or for the purpose of writing into it. For example, in each of this, on selecting one of these words, let us say word 15, we can write into it or read from it, and by placing the group of bits B0 to B7, and based on the operation R bar W bar, the read or write operation will go on. Of course, we can make use of a chip select to select this entire SRAM cell. Now we will have a look at how an SRAM basic cell works. Basically, it is a cross-coupled inverter logic. So let's say we have got two inverters, okay, which are cross-coupled. That is, the output of one of the inverter is connected to the input for another inverter, whereas the input for that inverter is connected back to the output of the previous inverter. So if this is how a connection is being done, and let us assume to begin with it has there are 2 points, okay, 2 outputs of this inverter, one we will call it as X, another as Y. Let us assume that the X is equal to 1, then this inverter will invert the value of X, which is 1, and produces a 0. Now Y takes the value 0, then this inverter will invert the value of Y, which is 0, and provide a 1, which is what is the value of X is. So this circuit shows that whatever may be the value of X, okay, it will remain stable as long as this inverter is being isolated from the external world. Okay, that is, these two transistors are off, then the value will be retained. On the other hand, when X is equal to 0, that value will also be retained as it is. So we will call one of the two signals X or Y as the value that is stored in this cell. Okay, let us call, by convention, let us call that the value of X is the bit that is stored. So we will call it as B, and the other value will be the complement of the same bit that is stored here. We will call it as B complement. So this is what we mentioned, that both the value as well as its complement will be available at any given time. We make use of two transistors for the purpose of selecting this bit cell. Okay, so this is called as the word line. When the word line is 0, then the gate signal to both these transistors are 0, and okay, it will not it will basically disable the X input to this lines, bit lines, and similarly Y input from this one. On the other hand, if the word line is 1, the transistors are on, and it enables a path between the X and Y signals to the lines B and B complement. Then by looking at the B and B complement, the value that is stored in this inverter circuit can be found out. Well, now how do we realize this cross-coupled inverter circuit? For that, we make use of 4 more transistors. Okay, in addition to the transistor T1 and T2, we need 4 more transistors, which we will call it as T3, T4, T5 and T6. So you can see that T3 and T5 together form a CMOS inverter. Okay, So T3 and T5 form one inverter, while T4 and T6 forms the another CMOS inverter. Okay, so one is an NMOS, another is a PMOS, and we will have the input to the inverters, which, for example, the input to this inverter is the input which is connected to these gates, and the output is taken at this point, okay, which is Y. Whereas for this inverter circuit, the input is the one that is connected to these gates and the output is X. We can easily see that it is cross coupled because the input of this inverter is connected to the output of the other inverter, and the input of this inverter is connected to the output of the other inverter, that is X. So basically it is cross coupled. Okay, and the way it works is actually if X is equal to 1, let us say, then what happens here is, so this is equal to 1, then this CMOS, if you look at it, this is an NMOS transistor which is being on and this is off. So effectively then there is an open circuit here and this is a closed circuit, and this will be connected to ground. Okay, so and in a similar manner this works. So which means that Y will become 0 and this is X, and because this is 0, then it allows, okay, it disables this, it offs this transistor, but this will become on and it is connected to V supply and this will become 1. This is the 1 is written. So it stores basically the value that is written into it. Okay, we will see how the writing operation can go on. Now, in order to read, for the purpose of reading and writing, we make use of this word line. When the word line is asserted, both transistor T1 and T2 will become on, and then we can do a read or write. The word read operation works is as follows. Okay, let us see. When we assert this word line, then this line will have X and this line will have Y. One of them will be 1, other will be 0. By sensing that, we will know what bit is present. But in order to, the charge that it will be difficult for these signals to drive the external sensing circuit. To enable that, we will pre-charge these two lines. By pre-charging, we mean bring it to a value which is halfway between 1 and 0. So once B and B bar is being pre-charged, okay, then we enable this word line so that T1 and T2 are both on, then B and B bar will be driven, okay. One of the bit lines will be pulled down, okay, and by sensing that one, by using an external sensing circuitry, the bit that is present can be read. In the case of writing, the value to be written is being given to the B and B bar lines. Suppose we want to write 1, B will be made 1 and B bar will be made 0. Then select the word line, T1 and T2 will be on, B and B bar will be put appropriate values, then it will force the value the X and Y to take appropriate value, so that the X will take the value of B, Y will take the value of B1. That way a bit can be written into the cell. We can have a simple SRAM sensing circuit, which is basically a differential pair. Using this, the bit can be sensed. The read and write cycle goes as follows. You place the memory for the SRAM timing. The address has to be placed in the memory address bus. Then for the purpose of reading, the read bar write control line has to be placed as 1, it goes 1. Then the chip has to be selected, CS has to be made 1. Then after a duration, call it as TAA, which is the time for purpose of for the memory to read, SRAM to read. The data will be available here, which can be taken outside. So this is the read cycle of an SRAM, and for the purpose of writing, again the address is being provided. R bar write bar is made 0, okay, and the chip is being selected. and the data to be written is being provided, whatever it may be, okay, F6 or whatever it is, if it is a byte, then you give some time for the data to be written, which is called as the write time TW, at the end of which you can be sure that the data is being written, and then it can be, control lines can be asserted back. From discussing the dynamic RAM, if you have any questions you can post. I will start answering your questions if there is any, and then we will continue with our lecture. You can also retain your question at the end of this session also. So there is one question that has been posted. What is the difference between SRAM and DRAM? As the name indicates, static RAM, as long as there is power, the value that is stored in each of these bit cells will be retained, okay, whereas the DRAM stands for dynamic RAM. It is dynamic in the sense that the value on that is stored will slowly get discharged, and therefore it is dynamic and it has to be refreshed. So this is the difference between SRAM and DRAM. But the advantages of the DRAM is that, okay, it is less expensive and therefore more bits can be packed in a given IC for a given cost, and that is the advantage. And SRAM is faster as compared to DRAM. So all these are also answered in the slide that we looking at, we will see right now. So when it comes to DRAM, the bits are stored as charges in capacitor. The charges leaks, therefore there is a need for refreshing even when there is power. But the construction is simpler because it is basically a capacitor which stores a charge. So it occupies less space in the IC and therefore it is less expensive, but there is a need for a complex refresh circuitry. But today we have, but that trade-off is acceptable under certain condition, but it is DRAMs are slower, okay, but it is mainly used to construct main memories of computers, whereas the SRAMs can be used to have cache memories. So this is a 3 transistor DRAM core cell. The transistor T1, okay, it is basically used to store the bit. It stores the bit as in the form of a charge that is as a capacitor and in the form of the charge that is stored in this capacitor. There are 2 other transistors, one connected to this write line and another connected to the read data line. So let's see what happens. So suppose this T1 has got some value being, charge being stored in this one, okay. If this value is 1, then this transistor T1 will be on. If we give a read command, read line is being asserted, then this transistor will be on, and you will see that the value of this transistor T1 can be read using this data line, read data line. In a similar manner, when you enable this write line, which will switch on this transistor and give the appropriate data on this write data line, then if it is 1, then this transistor will get charged through these lines and this charge will be retained even after you take out this assertion from this write line. So this way the value gets stored in this cell. To sum up, the value is stored on the gate capacitance of T1. What is the way the read operation works? When read is equal to 1, write is equal to 0, read data is being pre-charged. Again, a pre-charging is being to enable the read effectively. T1 will be pulled down and pull down the read data if 1 is being stored, okay. So T1 will, if 1 is being stored, then T1 will, then this transistor will be on, and therefore this, it will pull down this line and this can be sensed. In the case of write data, read is equal to 0, write is equal to 1. The data to be written is placed on the write data line, then the transistor writes the value but getting it charging the gate capacity. We can also construct a one transistor DRAM structure. Okay, the address lines basically is used to select the transistor which, okay, select the transistor which of this particular transistor. Then there is a storage capacitor which stores which denotes whether a value, a bit 1 or 0 is being stored. If the capacitance source the charge, then it is 1. If it has discharged, then it is 0. The write operation works as follows. The voltage to the bit line is being given. It has to be high if 1 is to be stored. It has to be low if a 0 has to be stored. Then this address line is being asserted. So this transistor turns on. Then if the B line is 1, then this capacitance gets charged through this conducting path, and a bit 1, then the capacitor gets charged. Then even after the address line is taken out, then the capacitance, the capacitor will retain that charge, but it will slowly leak. In the case of reading, address line is selected, the transistor is turned on, then the charge from the capacitor will leak through this path, through the bit line. Then by using a sensing circuit, we sense the value. Okay. However, but because the capacitor is getting discharged slowly, we have to refresh it. Okay. So the refresh circuit has to be needed, and it is normally included in the same DRAM chip. Okay. So during that one, you disable the memory array. Okay. Then read the content from each of this address location and then write it back. This is how the refreshing works. It takes time and it slows down the performance operation. So here shows a construction of a DRAM chip, which is a 1 megabit chip. So it is an array of 1K by 1K cell arrays, 1024 by 1024 cell arrays, each cell being a 3 transistor or a 1 transistor DRAM chip. There is a row address decoder that is present here. So there are 10 lines which come out from the address port of this DRAM chip. We have the row address strobe, column address strobe, read bar write line, and there is a control logic. Normally we first provide a row address line, which is these 10 lines A0 to A9 that is being provided. It's stored in this address in this register. The decoder decodes it and enables one of these location. Each of this row stores 1024 bits. Okay. So using this bus, which is of bit 1024, the 1024 bits corresponding to a given row will be available here, and here we have got a array of sense bar write amplifiers, 1024 such amplifiers. Each one of them will sense the bit that comes out in that column, senses it and amplifies it and writes it back into the same cell. So using this mechanism, a row can be selected, the entire row will essentially read and written back. So this is for one row. All the rows have to be written at certain rate, so that before the capacitor gets completely discharged, we will be able to read the bit content and write it back. So that is the rate at which refreshing should go on. This mechanism also helps for the purpose of reading or writing. Okay. So if you want to write a particular bit, then the corresponding bit location, the column address, is again being provided, and here you have to these lines. Okay. Here you have got a 2 muxes and demuxes. A 1 to 1024 mux is there, and 1024 to 1 demux is also there. Okay. So here we read an entire row and make it available in this register, and then by using a 1024 to 1 demultiplexer, one of the bits from one of the column is being read and we make it available outside, that is D naught. In the same manner, if you want to write a particular bit, having got the entire row into this register, we select a particular bit in that using this 10-bit column address and 1 to 1024 demux is being used to write a particular data that is provided in D1 to particular bit which is to be written. So the reading and writing can also happen using this kind of a circuitry. The timing diagram for DRAM is very similar to that of the SRAM, but only thing is here we provide the row address followed by the column address. So to begin with, the row address is provided for some time, and during this time the row address strobe is made available. So this is where the row address is being stored and the row is being selected and the content is being stored in the bottom register. Then the column address is provided in the same line A0 to A9. So these 10 lines will become available during this time. Then the column address strobe will basically allow these 10 lines, okay, present in A0 to A9 to select one of these bits, and that data will become available here. So now it is a read command that is being provided. So writing again involves by providing the row address first and enabling the row address strobe, which will enable one of the row, and then you provide the column address followed by the column address strobe and the data bit to be written, okay, the data bit to be written is provided and it goes to one of the locations and get stored in the corresponding bit. So this is the write operation. This data is being written. So well, now we will look at how memory modules can be arranged, okay, to form a larger memories, and how the way we construct larger memory using a number of memory modules will affect the performance of the entire memory. So this way of putting many memory modules to construct a larger memory is called as the memory interleaving. To begin with, we will have a simplistic view of a memory module. A memory module is one which has got an address port and a data port. An address bus is connected to the address port. A data bus is connected to the data port. Address bus is unidirectional. Data bus is bidirectional. You have a command to select the module. There are two commands or control lines, read and write. Okay. Well, now first we will see what is called as the high order memory interleaving scheme. So in this scheme, what we do is we divide the entire address lines into two groups. One, the high order lines, group of lines, and another the low order group of lines. Let us say we have got a total of H plus M address lines that are present. So if it is a, let us say, a 20-bit processor, then 20, if the address lines are 20, we can select 4 high order lines and treat it as the lines H, okay, and the lower order 16 lines can be treated as these M lines. Okay. The higher order lines, H higher order lines, are being used for selecting the modules, while the lower order lines are being used to select a location within the module. So what we do is, we will use a number of modules and each of this module is selected by using an appropriate decoding circuitry which takes these H lines as the input. There are H lines which are used for the module selection. So we can select up to 2 power H modules. These modules are numbered from 0, 1 to 2 power H minus 1. Let us say if H is equal to 3, then 2 power H, 2 power 3 is 8. We can have 8 modules numbered from 0 to 7. And the lower order lines, M lines, are connected to the address port of all these modules. Let us assume that there are 10 lines in this m is equal to 10, then 10 lines are connected to the address port, therefore the size of each of these modules is 1k. Putting it together, we will have 1k modules, 8 such 1k modules being arranged. Okay. So what is the advantage of this one? Here we can have a memory of size 8 kilo word memory. Okay. 8 modules each having 1k words, totally 8k words can be constructed. The important thing is successive addresses are mapped onto the successive location within a module, because we can see that supposing we fix the address lines are 0, 0, 0, then with that as 0, 0, 0, module 0 will get selected, then these 10 lines will change in all possible combination from all zeros to all ones and generate the addresses 0 to 1023. So all these addresses 0 to 1023 will get mapped onto the module 0. For all these addresses, the higher order 3 bits, H bits will be 0, 0, 0, and therefore only module 0 will get selected. So successive addresses are all mapped onto successive locations in this module 0. The moment you move to the location 1024, this H, the value of H, the higher order lines will become 0, 0, 1, and therefore module 1 will get selected and it will remain as 0, 0, 1 for the next sequence of 1024 locations. All those sequences, okay, will only select module 1, and a sequence of 1024 location will now be mapped onto module 1 and so on. So this is how the addresses gets mapped onto different modules in high order memory interleaving. So if you look at the general address that gets mapped onto a given memory module, if you look at the ith memory module, okay, then its starting address will be I into m, where capital M is the size of the memory module, which is m is equal to 2 power m, small m, 2 power small m. Okay. So for example, if you construct the 0th module, the starting address will be 0 into m, which is always 0, plus j. The j can take a value from 0 to 2 power m minus 1. So 0 to 1023 will be present in this module, 0 to 1023. Then the first module will have an I is equal to 1 and capital M will be 1024. So 1 into 1024 plus j, where j will again lie between 0 to 1023. So location 1024, 1025 onwards up to 2047 will all be present in the module 1. So in this way address gets mapped onto. This is the high order memory interleaving. This memory interleaving is the one that is commonly used in interfacing different modules onto the processor. The advantages of this one is that we can selectively add the modules, okay, in a progressive manner. If you want to expand the size of the memory, we can add one more module by connecting it to the appropriate address and data port and selecting the module select lines using a decoding mechanism. We have another module memory interleaving scheme that is called the low order memory interleaving scheme. In this scheme, what we do is we divide the total number of lines, m plus lines, into two groups, m and l, where l lines are of low order, m lines are high order. We connect all the high order m lines to the address port of all these memory modules. The L low order lines are used through a decoding circuit to generate the module select lines, and they are used to select the different modules. There are L lines in the low order which is used for the purpose of decoding. So we can generate 2 power L possible module select lines. So we can have 2 power L possible modules. We will call, let us call 2 power L as the capital M. So we can have module 0, module 1 to module n minus 1 or 2 power L minus 1. The address port of each of these modules gets the common lines which are the high order M lines. Okay. Now let's see how it works. Now if you look at this one, the lower order lines, okay, are being used for the module selection. Let's take a simple example. Let us say you have got in a group of 5 lines. We will take the lower order lines, okay, for the purpose of module selections. So let's say there are 5 lines which are in the address lines. So this will be L is equal to 2 and this will be M, okay, which is 3. Then the next address will be 0 1, 1 0, 1 1. For all these things, this will be 0 0 0, 0 0 0, 0 0 0. Okay. Now again we will have 1 0 0 and then 1 0 1. 1. So if you use this for the purpose of selecting module 0, whenever you have a combination of 0 0 in the lower order 2 lines, module 0 will get selected, which means it happens for this address and then it happens for this address, then it will happen for address which is 4 addresses after that and so on. So these are the addresses which will get mapped onto module 0. Okay. So address 0, address 4 and then address 8, these are the addresses that will get mapped onto module 0. The other way of looking at it, address 0 will get mapped onto the 0th location in module 0. Address 1 will get mapped onto the 0th address in module 1. Address 2 will get mapped onto the 0th location in module 2. All of them will be 0th locations. Address 3 will get mapped onto the 0th location in module 0 and then we will go on to the module 0 and so on. So addresses will get mapped onto in a cyclic manner, one after another. Okay. The generic address that will get mapped onto the ith module is that the initial address I will be the starting address of that module, then it will repeat after a gap of n. Okay. So it will be I plus nj, where j will be such that it will span the entire address space of that module. So j will lie between 0 to 2 power m minus 1. Okay. So what is the advantage of this kind of memory interleaving? We will see the advantage as follows. Suppose we give the m address lines to the address port of all these memory modules, and let us assume that all these modules are selected and we want to read successive locations from these modules. Okay. We give the read command also for all these modules. Then what will happen is, let us say if the address is 0, let us say on these m lines, okay, if all the bits are all zeros, then basically we are selecting the address 0 in each of this module. The address 0 in the module 0, address 0 in module 1 and all the way up to address 0 in module 2 power L minus 1. Then all these modules are selected and read command is given. So all these modules will start fetching the content of the 0th location parallel. After a time t, let us say t is the time it takes for all the memory to fetch the content. The data will be available on the data port of all these memory modules simultaneously. Then we can latch it onto an output latch of these connected to these data ports of this memory module. So parallelly, okay, all memory modules can be used and they can be used to fetch the data parallelly, and effectively in a duration of t, we can have up to n references go on in parallel, which means the effective time it takes to fetch a data is t by n, because n data items in a duration of t, effective access time to fetch a data is t by n. So all access will go on in parallel. So now what we do is we change the address to the next location 0001, okay, these are all higher order. Then all these modules will start fetching data in their address location 1 parallelly and provide it after a duration of t. Before that, the first set of data which are being fetched and stored latch here have to be taken out using a router circuitry, mux circuitry here. So it will first take the address 0, data 1, data 2 and up to data 2 power n minus 1. By the time it gets over, a new set of n data will be available which will be stored and so on. So effectively this can act as a very fast memory which is n times faster, and for a sequence of memory accesses to be done in successive location, data can be fetched at a rate of t by n. So we say that the effective access time is just t by n. This is true when we are reading locations which are successive in nature. Many times we have to read locations which are not just successive in location. We want to read data at locations which are at a constant distance from each other. That is location 0, 2, 4, 6 or location 0, 3, 6, 9 or 0, 10, 20, 30 and so on. That basically comes because when we store a two-dimensional array row wise, the first row of let us say a 10 by 10 array in memory, you can store the first row in successive location followed by the second row and so on. So the first row of 10 elements will be stored in the first 10 locations, then the second row will be stored and so on. If you want to read it column wise, okay, then we have to read elements which are present in the location 0, 10, 20 and so on, which means you have to read locations with a constant skip distance. Skip distance in this case is 10. So based on the size of the multi-dimensional array, we have to read locations at certain constant skip distance. Now let us look at how this low order interleaving will work for different skip distances. Let us assume that we have got a low order memory interleaving scheme where we have got 8 modules. The modules are numbered as 0, 1 up to 7. Let's see how addresses gets mapped onto this one, because all those addresses which have got the lower order bits, 3 bits equal to 0, 0, 0, okay, will get mapped onto memory module 0, because the memory module 0 will be selected if the lower order 3 bits are 0, 0, 0. So those addresses for which the lower order bits are all 0, 0, 0 or 0, 8, 16, 24 and so on. Okay. So the addresses will get mapped onto in successive modules as follows: the address 0 on 0, 1 to 1, 2 to 2 and so on up to 7. Then the 8th address will get mapped onto 0 and so on. So this is how the addresses will get mapped onto 8, 9, 10 and so on, and then 16 will again get mapped onto the module 0 and so on. So if you want to fetch data with a constant skip distance of d is equal to 2, which means the access pattern of the addresses are as follows: 0, 2, 4, 6, 8, 10 and so on. So we will see to what modules these addresses gets mapped onto. So if it is 0, 2, 4, 6 and then 8, 10, 12, 14, this is how it gets mapped onto. So we will see that 4 addresses maps to 4 modules, and the next set of 4 addresses will get mapped onto the same 4 modules and so on. Effectively, there are modules which are never need to be accessed because none of these addresses in the sequence get mapped onto those things. For example, odd numbered module 1, 3, 5 are of such a nature that no address gets mapped onto and they are not needed. But even numbered modules are required. But at any given time in one cycle, only 4 modules can be used. Okay. For the next set of 4 modules, you have to wait for another cycle of duration t. So in a duration of t, not 8 but only 4 accesses can be done in parallel, and therefore the effective access time is 2 into t by m. M in this case is 8, so it is 2 into t by 8 or t by 4, because only 4 accesses in a duration of t. So this is what happens in when we have a skip distance of d is equal to 2. Now let us case a case where the skip distance is 3 and we have got 8 modules, okay. Then the access sequence will be like this one: 0, 3, 6, 9, 12, and there will be of course a 15 will be there, which is missing here, 18, 12. And let us see to modules to which that get mapped onto. 0 will get mapped onto 0, then it will be 3, then it will be 6, okay. So we will see 0, 3, okay, 6, and then the 9, then we will be 12, okay, then it will be 15, then it will be 18, 6 is there, yeah, then it will be 21. This is how the pattern gets mapped onto, which means over a sequence of 8 accesses, they all get mapped onto different modules. So there is a potential parallelism of using those modules. But there is only one problem in these accesses: the higher order, okay, lines will differ for this group from this group. Therefore, we cannot access all these modules at the same time. We can only effectively access 1, 2, 3 at a given time if you provide the common set of high order address lines to all these modules. Then we have to wait for another cycle and provide a different set of address lines for this address port and so on. Okay, so this is how we can do it. So in this mechanism called as the simplex low order memory interleaving, if we have a skip distance of s, then the effective access time will be t by n into s, okay. So in this case t by 8 into 3, okay, will be the one. As long as the skip distance is less than n, this is okay. If it is more than n, at any given time only one module can be fetched. Well, we have a different scheme called the complex interleaved scheme, wherein what we do is the different addresses that are being generated by the processor are being looked upon by the memory controller. We have different memory modules which has got both a buffer at the data port as well as the address port. For every address that we get, we just check to which module it gets mapped onto, check whether the module is busy or idle. If it is idle, we place the address on this address bus and latch it onto the corresponding address buffer and give the read or write control. After a duration of, then the module will become busy, which will be asserted by this module. When the fetch is complete, that is after a duration of t, then the module will imply it by making this as idle. So whichever module that have completed, what we do is we can transfer the content of it through this common data bus. So in this manner, as long as the addresses gets mapped onto different modules, parallel access can be made possible using this complex low order memory interleaving. And in particular, it can be shown that if n, the number of memory modules, and s, the skip distance are relative prime, then effective access time is t by n. Now we will move on to a different topic, which is called as the memory hierarchy. We saw that we have got memory of different technology. We only saw two things, the SRAM and the DRAM, both are semiconductor memories. We also have memories which use different technologies for storing bits, magnetic storage devices like hard disks, optical storage devices like CD-ROMs, DVDs and so on. So there are memories with using different technology for storing bits. They have different characteristics. Some of them are slower, some of them are faster, and some of them are costlier, some of them are cheaper, and so on. So we would like to have a memory to be interfaced with the processor, which meets certain criteria. What are the criteria we generally looking for? We want a memory which has to be very fast. We want a memory which has to be very large. We want the memory to have a cost which is reasonable. So this cannot be met by only one memory from a given technology alone. If you only have a memory which is a semiconductor memory, it is costly, but you can't have a large sized memory for a reasonable cost. If you just use a memory which is based on optical storage device, very large memory can be had, but it will not meet the bandwidth requirement of the processor. So what we do is we have to have a hierarchical memory structure wherein we draw memory from different technology and put it in a hierarchy which meets the requirement. So we need a fast buffer memory that can gap the speed gap between the CPU and memory. Okay, fast memories are expensive, but they are not large. So we use a second or third level memory, okay, which can store more data, but and which are also cheaper. So a memory hierarchy just you can be viewed to have a pyramidal structure, so that at the bottom, at the lowermost level, we use technologies like magnetic tapes, okay, and so on. Of course, these days we don't use those things, but hard drives can be there. Then you can have optical discs, okay. Then you can have fixed rigid discs like the hard disks. Then you can have semiconductor memory, okay, that is we call generally as the main memory, which uses the DRAM technology. Then you can have levels of memory, which we will call it as the cache memory, generally following the SRAM technology, which can have one or more levels. Then you can have registers within the processor and so on. So this manner we can keep it. So this generally shows the order of the access time of these bits that are being stored. This is a 1 to 2 nanoseconds, 3 to 10 nanoseconds and so on. As compared to that one, we can see that memories, which we will call it as the secondary memory later on, the order of access time is in terms of millisecond. Okay, so we can see that if you have n levels of memory, okay, wherein we will call the 0th level will be the one which is closer to the processor or the cache memory. The nth level is the secondary memory, that is the optical storage devices, okay, which will be farther away from the processor. Farther away means before fetching a data from the nth level, we have to go through all the level lesser than that. First look at the first level, if it is not present, go to the second level and so on. This is how the access will keep happening, okay. So if you look at the ith level of memory, I lying between 1 and n, okay, and attribute the different characteristics of the memory in terms of the cost, size and so on, we can, these are the characteristics that are exhibited by memory. Let us assume that Ci be the cost per bit of the memory at the ith level, okay. For example, the cost per bit of a memory, okay, in the SRAM may be, for example, okay, 1 rupee per bit and so on, okay. But in the case of the optical storage device, it will be 0.0001 rupee and so on. So there will be a wide gap between the cost per bit. Similarly, the effective access time or the average access time in seconds of the ith level, let it be Ti. The size of the memory in bits of the ith level be represented as Si. Then there is something called as the bandwidth, the number of bits that can be accessed per unit time by a given level. Let that be Bi, okay. Then the granularity of access. In one cycle, how many bits are being accessed? 1 bit or 1 byte or 16 bits or a block of size 1024 bytes and so on. Because some of the secondary memory storage devices are block oriented devices, okay. You can only do a transfer in terms of blocks or sectors, okay? So that decides the granularity. So with this as parameter, we can write the general characteristics of memory hierarchy as follows. Ci is usually greater than Ci plus 1. That is, the cache memories are generally having higher cost per bit as compared to the main memory, because the cache memory is of I is equal to 1, main memory can be the second level cache or the main memory. Cost per bit will be, as we go closer to the processor, it will be costlier. Access time of ith level will be less than the access time of the I plus 1th level. More you go closer to the processor, you will be faster memories. Then the memories which are closer to the processor will be generally smaller in size as compared to the memories which are farther away from the processor, and so on. Even the bandwidth will also be larger for memories which are closer to the processor. Okay. So, in addition, how the memory is accessed is as follows. Whenever a processor generates a request, you first check the ith level, okay, where in the access pattern of 1, 2 up to n. So, you first look for the data whether it is present in the level 1, which is the first level cache. If it is present, you read from it. If it is not present, we say it is a miss in the level 1. You go to the level 2 and check whether the item is present. If it is present, which we will call it as an hit, you take it, otherwise you go to the main memory and so on. So, this is how the access is being made. Then the way the data gets stored has to obey some property. One property is called as the inclusion property, which is generally obeyed, but in certain cases it can be relaxed. What it says, the inclusion property is the address space of the level I is a subset of the level I plus 1, which means whatever the data that is present in level I should also be present in level I plus 1. In other words, the content of cache level 1 will definitely, all those data should be definitely present in the level 2 cache, and all the contents of level 2 cache should be present in the main memory, and the content of the memory should be present in the secondary memory, and so on. So, the level I is a subset of level I plus 1. So, this is what we call as the inclusion property. But the data in level I, okay, which corresponds to the same data in level I plus 1, okay, can be in different addresses. Okay, the way it gets stored can be different, but the data should be included. Then we have another property called as the coherence property. That is, different copies of the same data present in different levels should be identical. Otherwise, if the copies of the data are different, then we say it is incoherent. Okay, then we will not know which would be the right one. So, all copies should be identical, but the incoherency can be allowed for some time for the purpose of efficiency, but eventually you should see to that either the processor or from the external device that accesses, we should access the coherent data. Okay. Then how do we pose the memory hierarchy design problem? That is, let us call the by HI the hit ratio of the ith level. What it means is, for the probability that an arbitrary memory request that is sent to the ith level is being satisfied by the ith level, that we call it as the hit ratio. Okay. Then obviously 1 minus HI is called as the miss ratio, which is the probability that an arbitrary request cannot be met by the ith level. Normally it will so happen that the first level cache should have an hit ratio of the order of 0.9, second level cache may be of 0.97, and the main memory 0.99. So, this is the kind of the hit ratio we would generally try to achieve. Then there is an access frequency. How much time do you really go to the ith memory in order to fetch an item? You will go to the ith level only when level 1 to I minus 1 have miss, and therefore you go to the ith level. So, Fi, the frequency of access to the ith level, can be written as 1 minus h1 into 1 minus h2 and so on, 1 minus hi minus 1 into hi. So you will access from the ith level only when there are misses in all the levels lesser than I and there is an hit in hi. So what is the effective access time? So when you go to the ith level and fetch an item, then you have to spend a time which is equal to capital Ti. Let small ti represents the time it takes to access an item from the ith level. Then if you have to go to the ith level and fetch an item, you should have searched in all lower levels also. Therefore, capital Ti, the time it takes to fetch an item from the ith level, includes the access time of all lower levels and the ith level. That is why we write it as sigma I varying from 1 to I, small ti is capital Ti. Then the effective access time from the n level memory hierarchy can be written as sigma I varying from 1 to n fi Ti, because fi is the fraction of the time you go to the ith level, and if you go to the ith level, the time it takes is capital Ti. So the effective access time it takes by the hierarchy is sigma I varying from 1 to n fi Ti. What is the effective size of the memory? It is just the size of the nth level. It is not the size of all the levels put together, because of the inclusion property. The content of the nth level is present, okay, a part of it will be present in n minus 1 and so on. The first level will be duplicated in the second level will be duplicated in the third level and so on. So the effective maximum amount of data that you can store is just nothing but the size of the nth level. Okay. What is the total cost of the memory hierarchy? If Ci is the cost per bit in the ith level, if Si is the size of the ith level, sigma I varying from 1 to n, Ci Si is the total cost of the memory hierarchy. So now we have got a formula for the total cost of the memory hierarchy, the effective access time, the total size. So what we want in the memory design problem is, we want a memory which is very large in size. Okay, that is Sn has to be very large, reasonable cost, this cost has to be reasonable, okay, and low effective access time. This T should be very close to, it should be in between T1 and T2, the access time of the cache, first level and second level cache, somewhere in between. So this is the problem we will face in designing memory hierarchy. So with this, I will stop this lecture for this session. We have covered the memory hierarchy as well as the memory technology. We will take up the cache memory design and also start with the main memory. In the third lecture series, we will cover the main memory design, that is the concept of virtual memory, and the IO design. This is the organization of the lecture series for the next following lectures. Now I welcome, if you have any questions, you can post it. So I will take up questions one after another. SRAM, each bit requires 6 transistor circuit. Why is that? Because as we have seen, we need, it stores a bit using a cross coupled inverter. Each inverter requires 2 transistors, 2 inverter requires 4 transistors, and the bit enabled lines require 2 more transistors. Put together it is 6. Yes, Ram, sir, is the address multiplexing working is the same as the working of the mux and demux? This mux and demux, okay, it also has to use this mechanism. Okay, what basically a mux will do is that based on given a particular select line, it will select one of the different input lines and connect it to the output line, for which it needs a decoder. Of course, there has to be a decoding mechanism present in the mux also. Then in the construction of a 64K, is the random selection of the row and column. There is a time lapse between the between the NOT gate that is placed in the SRAM, and if yes, then how much? I am not clearly getting your point, because of course there is a gate delay that are involved between enabling a line and the bit being available. That is what together will constitute the access time of a chip. Whether the level 2 cache is faster than the level 1 cache? No. Level 1 cache is usually faster than the level 2 cache. Which RAM is not as fast as SRAM, but is cheaper? Okay, DRAM is cheaper than SRAM and is used in the main memory. DRAM is cheaper because it requires lesser number of transistors. Purpose of interleaving scheme does not help in deleting data from the memory or not. Interleaving is a way of organizing the addresses. Okay, it will not delete any data. It has nothing to do with, by interleaving will not delete any data. It is a way of organizing data and reading or fetching from it. Whether 0 of the level 2 cache is fast, that we have answered. Why not we can enlarge the size of RAM? Yeah, RAM size can be enlarged by using the same mechanism. We can have a larger row and column decoder, and we can have a larger sized RAM. What is the mechanism of unidirectional address bus? Why not it is capable of working like a bidirectional bus? Address has to be unidirectional because an external device has to place the address and indicate what address it wants to access, read or write. So the address bus has to be unidirectional. There is no need for it to be a bidirectional one, unlike a data bus. Can we use any other instead of transistor? Now, normal, because most popular technology is the CMOS technology because of the low cost. Okay, and that is why we most of these DRAMs are constructed using CMOS technology. What is the trade-off between granularity and bandwidth? So there is no actually trade-off between bandwidth and granularity. Granularity is because by its own nature certain devices can only transfer bits of larger quantity, because it is fetching data in terms of transferring data in terms of larger blocks. Okay, for example, if you access, in the case of an hard disk, it is not meaningful to access a particular byte. You position the read arm to a particular drum and then access an entire sector together into a RAM and then do operation. So that is what decides the granularity. Bandwidth is closely related to the access time of the memory. Among high order and low order memory interleaving, which one is the most commonly used? High order memory interleaving is the one that is commonly used. Low order memory interleaving is used only if the speed of the memory is not sufficient and if there is a potential parallel access that is required. Which is the coherence property implemented in the memory for storing data? Yes, every memory hierarchy has to satisfy this coherence property. We are going to deal with that extensively when it comes to the cache memory. We cache the main memory update policy. Okay, will solve this coherence policy. You may use a write back or write through policies. In write through, all the time the data is consistent. In write back, we keep it inconsistent for some data for the purpose of efficiency, but eventually we have to update the main memory content. We will deal it in length later. First question: in dynamic RAM, when a data is fetched, how is the capacitor is being recharged for the next access? As I mentioned, the refreshing has to be done at a constant rate. Okay, this is important for the data to be retained. While it is reading immediately, while after sensing the data, the data is being written back to it because the capacitor is discharged in the process of reading. While is the Little Indian a popular choice between the two? It's not, there is no distinct advantage of Little Indian as compared to the Big Indian. Okay, Probably I think little India, Intel started using Little Indian, so because Intel processors are more often used, Little Indian is popular. There is no other particular advantage of Little Indian way of packing as against Big Indian. Okay, I think because there are no other questions that are being posted. Okay.